Welcome to our lesson on the Lensmaker's equation. In optics, the Lensmaker's equation is a fundamental formula that allows us to determine the focal length of a lens based on its physical properties. It's a powerful tool for optical design and understanding how lenses work. Let's break down what each term in this equation means. F is the focal length of the lens, which is what we're usually trying to find. N is the index of refraction of the lens material. This tells us how much light slows down and bends when entering the lens. For glass, this value is typically around 1.5, while for water it's about 1.33. R1 is the radius of curvature of the first surface, which is the side where light enters the lens. R2 is the radius of curvature of the second surface, where light exits the lens. It's important to understand that these parameters follow specific sign conventions in optics. Now, let's discuss the sign conventions, which are crucial for correctly applying the Lensmaker's equation. For the radii of curvature, if the center of curvature is to the right of the surface as seen from the incoming light, the radius is positive. This creates a convex surface as viewed from the incoming light. If the center of curvature is to the left of the surface, as seen from the incoming light, the radius is negative. This creates a concave surface as viewed from the incoming light. For the focal length, a positive focal length indicates a converging lens, while a negative focal length indicates a diverging lens. Let's visualize the two main types of lenses and their effects on light rays. A biconvex lens, where both surfaces curve outward, is a converging lens. Parallel light rays passing through it converge to a focus point. A biconcave lens, where both surfaces curve inward, is a diverging lens. Parallel light rays passing through it appear to diverge from a virtual focus point. Now, let's work through an example to see how to apply the Lensmaker's equation. Suppose we have a thin glass lens with an index of refraction n equal to 1.50. The first surface has a radius of curvature, R1 equal to positive 20.0 centimeters, making it convex from the light's perspective. The second surface has a radius of curvature, R2 equal to negative 20.0 centimeters, making it concave from the light's perspective. Our task is to find the focal length f of this lens. Let's visualize this lens first to understand what we're working with. Now, let's solve for the focal length using the Lensmaker's equation. Step 1. Write down the Lensmaker's equation. 1 over f equals n minus 1 times the quantity 1 over r1 minus 1 over r2. Step 2. Substitute our values. 1 over f equals 1.50 minus 1 times the quantity 1 over positive 20.0 centimeters minus 1 over negative 20.0 centimeters. Step 3. Simplify the inside of the parentheses. 1 over positive 20.0 minus 1 over negative 20.0 equals 1 over 20.0 plus 1 over 20.0, which equals 2 over 20.0 or 0.10 per centimeter. Step 4. Calculate 1 over f. 1 over f equals 0.50 times 0.10 per centimeter, which is 0.05 per centimeter. Step 5. Find the focal length by taking the reciprocal. F equals 1 divided by 0.05 per centimeter, which gives us 20.0 centimeters. Let's interpret our result. We found that the focal length is positive 20.0 centimeters. A positive focal length means this is a converging lens, focusing incoming parallel rays to a point 20 centimeters away from the lens. Let's visualize how light rays would travel through this lens. Understanding the Lensmaker's equation is essential for designing optical systems like cameras, telescopes, microscopes, and eyeglasses. It helps engineers create lenses with specific focal lengths to achieve desired optical effects. In summary, the Lensmaker's equation allows us to calculate the focal length of a lens when we know its material's index of refraction and the radii of curvature of its surfaces. To use the Lensmaker's equation, 1. Identify the index of refraction of the lens material. 2. Determine the radii of curvature for both lens surfaces, being careful with sign conventions. 3. Apply the equation. 1 over f equals n minus 1 times the quantity 1 over r1 minus 1 over r2. 4. Solve for the focal length f. With this powerful equation, you can analyze or design lens systems for various optical applications. Try working through more examples to gain confidence in using this essential optics formula.